Okay, welcome back. We're going to be working on a 3-bit comparator that we started designing in the previous lecture. You should definitely watch all of the previous videos at least once to make sure you understand what this design is doing. It is becoming too much material to recap at the beginning of each video. However, what I will point out is at this moment in time, we have successfully designed a 1-bit comparator with these inputs in order to fulfill the truth table shown here. Our goal now is to use this 1-bit comparator that we have designed and tested to build a 3-bit comparator, where if the largest bits are equal, it will mean the next pair of bits need to evaluate. If they've determined it's greater than or less than already, we will simply propagate the less than or greater than output to the very end. So let's go back to Vivado. And we will see that I have created a design file. You can't actually see that right now because I'm currently looking at waveforms. So what I want to do is I want to go ahead and bounce over to the Sources tab next to Scope. And then I would actually like to close my simulation. You will see at the top this blue simulation bar. I'm going to follow it to the end and click the blue X and click OK. That now is the simulation is closed, which means I will be able to run another simulation later. I will then double click on this comparator 3-bit, which I created, if you recall, using the Add Sources button, making sure that it is a design source. When I double click on it, I open it up to the default template. Something that I will say at this point in time, when you create the Add Sources button and you go create design sources, you can create multiple files in here at the same time. In previous versions, including 2020, if you created multiple design files at the same time, only the first one that you create will have this predetermined template. 2022 appears to have fixed that issue. Just like when I created the comparator 1-bit, the first thing that I need to do is describe to the outside world what the ports and connections are going to be. We can do that by looking at the block diagram that I created earlier. So here, we're going to need a 3-bit input for each of X and Y, a 1-bit L in, a 1-bit L out, and may as well create a 1-bit G out. So I'm going to have X and Y. These are going to be inputs. So I do X, Y, colon, in. But this is going to be what's called a standard logic vector. This is a vector of standard logics, meaning it can contain multiple ones and zeros. However, I have to specify the size. The size is going to be 2 down to 0. The reason for this is VHDL is 0 indexed, so that the smallest bit is 0. The down to notation means that the largest bit, the most significant bit, aka the MSB, is on the left side. I can write 0 to 2, but that would be a reversed number and is harder for us humans to read. If you ever receive an error as you are designing things that says signal cannot be unconstrained, it's because you created a standard logic vector or an unsigned or signed number that does not have a size associated with it. The next input that I need are the LI input, as shown here. The standard logic vector created y2, y1, y0, x2, x1, x0 as part of those indexes. Now I need the LI. Oh, and not pictured here, I have forgotten, because this is an older version, that I also need the GI input. These are simple standard logics. Lastly, I need to handle my output, which I have called G out and L out in that previous diagram with the direction of output and of type standard logic. The next thing that I need to do is I need to make the 1-bit comparator accessible to this design file. I do that similar how I did it in this test bench, where there's this component declaration. Well, I need a component declaration. I could copy and paste this. However, I would like you to remind you to the method that I prefer, which is I go to the entity, I select it, I push Control-C to copy, I come back to the 3-bit, I select the architecture header, which again is between the architecture statement and its begin. I push Control-V to paste, I change the word entity to component, and then I change the end statement to end component. This has made the comparator 1-bit available to use in this new design file. Also recall from the previous video that I have signals that are associated with these ports available to use. However, if I have any signals that are not associated with ports, that means I will need to explicitly make them available to use, which will also be done in the architectural header. The signals that I will need then are this signal here, which is the greater out, and this signal here, which is another G out, this L out, and this L out. So I need a total of 4 signals. There are 2 acceptable ways to do this. Is one, I could create them as vectors. So I will say, I need a new signal. This is like creating a variable in most other programming languages, but in VHDL, it is a signal. That signal I'm going to call G, this is the greater than, so G S, the G signal, underscore 0, and G signal underscore 1, where this will be GS1 and this will be GS0. I could specifically on my diagram add names to those signals so that I know what they are later. Unfortunately, it doesn't quite fit, but you get the idea. Oh, sorry, I said this was going to be GS1, which is important so that I remember where things belong. Alternatively, well, oh wait, let me finish this statement, sorry. These are standard logics because they're attached to standard logic ports. I also need a signal for the LI ports. However, I'm going to create these slightly differently, which is I'm going to have an LS, which is my LS signal, that are standard logic vectors, 1 down to 0. These are creating equivalent signal concepts. It's just that one of them I'm broken into standard logics and one of them is bundled together in a standard logic vector. I will use each of them in this design to show you how you might use them in your own designs, and you can choose which way you prefer. Much like the previous design in the test bench, I need to create a port map, which is also called a component instantiation. This is the component declaration, which says it is available to use. Now I need the instantiation, which says I'm going to use it, and here's how it's connected. The easiest way for me to do this is to go to the test bench waveform, or the test bench simulation file, and I'm going to just copy and paste that previous, because I've already created a port map, which is honestly a lot of typing. So Control-C, here, Control-V. I'm going to do another thing that is entirely optional, which is to, sorry, I got sidetracked with these errors, which I will address in just a moment. But recall from the previous lecture, I have described 2 different types of VHDL architectures that we will be designing. One of them, from the comparator, was behavioral. This is a description of how a 1-bit comparator behaves. However, the 3-bit comparator has no behavior. It is just a description of how 3 of those 1-bit comparators connect together. So I am going to change behavioral to structural. Structural VHDL is how things are connected together. However, this is simply a name, and it does not strictly enforce that this is structural design. If I make this change, I need to go and change end structural because it is a different name. I could call this Bob and it would work just fine, but it is better to use descriptive words. Next, I would like to point out that these signals are unhappy. If I mouse over, you will see the error X_TB is not declared. That's because this XTB signal does not exist, whereas in the test bench file that I designed, I explicitly called a signal XTB. Well, in this case, I'm not using test bench signals, I'm using design signals. And it is not UUT because this is no longer a unit under test. If you go look at my design, I've decided to call this comp2, meaning this is a comparator that is comparing the index of x and y at index 2. So I will rename this to comp2. I'm going to realign my ports because I genuinely believe this makes the code more readable and therefore easier to debug. But now I need to connect X to something. At this point in time, I hope you don't fault me if I change my mind in order to make this more readable from XY to AB. This is just changing essentially the variable names so that they're a little bit easier for you to read. So I'm going to map the signal A at index 2 to the port X of my comp2 bit. That's connecting this signal, which I'm now calling A2 instead of X2. And I'm saying it's the second bit of a 3-bit signal called A. I do that by here. I've connected the signal A to my first comparator's X port. I am then going to connect B, also at index 2, to Y. So I'm now comparing A at 2 to B at 2. There is now a GI and LI input. These are directly from those inputs, GI, LI. I'm using those signals that are associated with the ports. However, for this next line, the GT is not connected to the entity's Gout port because it is this internal signal that is connecting two components. So I need to create a new signal, which for the GT is GS1 as shown in the picture. I have now connected a signal called GS1 to the port GT. I will now connect the LS signal at index 1 to the LT signal. Excellent. I'm going to utilize my favorite copy and paste to make another one of these. However, there's an error. If I mouse over the error bar, it says comp2 is already declared in this region. That is because I cannot name two different things the same name. This is now comp1 as shown in the block diagram. Great. Now I have to update this port map because otherwise this is just two of the same device. I've wired them up what's called in parallel. Instead, I want them in series where the outputs of the first comparator are connected to the inputs of the second comparator. So I'm now going to take A and B at their index 1. Instead of GI, which would be the port coming in at the entity, which would be problematic, I instead want to take GS1, which is the output of my previous comparator, and plug that into the input of GI. Similarly, I want to take the LS output and plug that into the input of the LI. Those two code changes have made this connection and that connection, connecting the output ports to the input ports. Lastly, I need to update the outputs because specifically I cannot have two different devices telling one signal what to be, because if they disagree, one might output a 0 and one might output a 1, and that will create a broken device, which is problematic. So my new GT output, if we look at the device, is now what I have decided to call GS0. So we're really just updating the input or the outputs. So this output is now GS0, or in the case of LS, I'm just updating the input to LS0. Lastly, I'm going to select, push Control Z and Control V, and again, simply update the index. Again, the output of the previous one should be mapped to the input of the new one. This error again is because I need to change this name to comparator 0 because VHDL is 0 indexed. The output is GS0, which means that connects to the input of the new device. The output was LS0, which again connects to the input of the new device. Lastly, the outputs. These outputs actually connect to the output ports. These ports, which I have called G out and L out. You can double click on this to scroll up and make sure that it highlights the port. If you ever see an output from a port that is U, that means undefined, and very frequently means that you did not connect one of your signals in your port maps here at the structural level to the actual output ports of the higher level entity. So I would go in, double click the output that would have a U and scroll down and make sure that at least one of my output ports of an interior device is assigning to G out. In this case it is, and I have a reasonable degree of confidence that I have successfully designed a 3-bit comparator, assuming that this picture matches the intended design. However, if we want to determine that, we are again going to turn to a test bench. The test bench will be the topic of my next video, and I will be introducing more advanced test bench techniques because this test bench is going to be more complicated.